All right, all right. Giving a little recap of what you've done. Okay, so you missed that. You saw the video, right? Okay. The last thing we were talking about was interference, right? So what is interference? When two light sources, what are the conditions required for them to cause interference?
The two sources should be coherent.
They should be coherent.
The wavelength should be in a visible region.
Mm-hmm.
Wavelength should be as large as possible. The length, which is the slits to screen length, should be as far as possible.
Mm-hmm.
And D should be as small as possible.
Good.
Being the separation.
Perfect. There you go. The most important thing is they should be coherent, and then all those conditions will make the interference fringes visible. Okay. Now I also told you about how Newton's rings are formed. Right? So what are Newton's rings?
When you look down
When you look down at, let's say, a convex lens sitting on a glass plate, light going down, hitting the bottom of the convex lens, bounces off, and then the other one goes down to the bottom of this one and then bounces off. These two rays suffer a path difference, and according to the conditions for interference, if the conditions satisfy for destructive interference, then it will be dark. And if the conditions satisfy the condition for constructive interference, then it will be bright. But there is also something I told you about phase changes, right? How much is the phase change at a denser medium?
Lambda over 2.
Phase change is pi, but path change is lambda over 2, that's right. Path change is lambda over 2, phase change is pi. And at a rarer medium, what's the phase change?
Sure.
0. No phase changes there. So considering the phase changes also, what will you see right at the middle where there's no path difference at all? It should be dark. It should be dark. There's no path difference here, but because of the reflection from a denser medium and a rarer medium, there is a phase change. And that makes the central part of it dark. So you have a dark patch in the middle, and then you have rings, dark rings that goes around like that, and those are called Newton's rings. Yes.
What is the phase change into a rare medium?
On a rare medium? Nothing.
Into a dense medium, it's
On a dense, not in. Oh yeah. What you said, into?
Yeah.
Yeah. On means like if this is a dense medium, if you're having a ray going and bouncing on it, then it suffers a pi phase change.
And then from a rare medium or on a rare medium?
On a nothing. So on a dense medium, so this is dense, there is a phase change. So if it goes and hits like that, it bounces back that way. That's what happens on a dense medium. But on a rare medium, goes and hits here, and then it comes back the same way. No phase changes.
And then the path difference in a dense medium is lambda over 2.
Oh yes. So when you talk about a phase change of pi here, the phase change of 0 here, this corresponds to a path of lambda over 2, and this corresponds to a path of 0. The path difference is going to be 0 here, and there's the lambda over 2, right? And considering this feature also over here, the central one, instead of being bright, is going to be dark, right? I asked you to look at Newton's rings online, so did you watch it out? Did you check the Newton's rings?
Yeah.
I'll pull it up right now. Yeah, so there we go. This is Newton's rings by a transmitted light. Yeah, that one. Yeah? So what is in the center is black, right? And then you have yellow ring. And then again dark ring. And again yellow ring. Why are those in the shape of rings? Why are those in the shape of rings is because the locus of all the points around the lens that will have the same path or same thickness, if you take the locus, it's going to be a circle. That's why you have Newton's rings, like circular rings going around, right? Now, as you saw in this picture, it was yellow in color. So what was the color of the light used? Yellow. One wavelength. It's monochromatic. And that's the reason why you saw it as dark and yellow, and again dark because it's destructive, and again yellow, and again dark, yellow. So it's between, it's dark, yellow and black. It's yellow and black. That's a pattern that you saw. If you used colored light, yeah.
Can you repeat why it's dark right in the center? Why there's
Okay, now at the center, physical path difference is 0. But because of the difference between a rare and a dense medium reflection between these two rays, it creates that much path difference.
Oh, okay, because the bottom is a dense medium and the lens is a rare medium?
Yeah.
Okay.
Exactly. And so even though there's no physical path difference, there is a phase change already created. And that is what makes this one, instead of being bright, dark. Okay? That's why you saw that Newton's ring. Now, what will happen if you use colored light, which is white light? If you use white light instead of monochromatic light, what will be seen as rings? What will you see on the rings?
Red farther away and blue closer?
Yeah. So what exactly will happen? It's going to be a complex image. Now, what is going to be seen is, because you're using different wavelengths, you have smaller wavelengths, you have larger wavelengths, like different wavelengths coming through. That means at any spot, some colors will meet destructively, and some colors will be constructive. You understand? So some colors at this spot will meet destructively, and some other colors, because of their wavelength, they will meet constructively. So what is the result? The result is going to be, at any spot, you're going to see some color or the other.
Whoa.
You get it? It's not going to be dark anywhere. If it is dark for red, then other colors could be having some intensity. You understand? So when you look at Newton's rings under white light, you will see beautiful colored rings. The center will be black.
Can I look that up?
Yeah, you can look. Okay, I'll look it up. Yeah, look it up. Just type in Newton's rings with white light. Newton's rings with white light. Check it up and see, and let me see. Newton's rings with white light.
That is pretty.
Do you see it?
Yeah.
Let me see. Yeah, there you go. That's pretty much what you see if you use white light.
That's awesome.
You get it?
What is it? Should it be with white light? Would it be dark in the center?
Yeah, I think it's because
Because all the colors are.
we can just take that, not it, we can make that. That's the thing.
It's pretty cool.
We can make what?
If you just have a lens and rear.
Oh yeah, we can make it. I actually used to set it up. It is a troublesome thing, to set it up. I use the microscope, and I put this thing. It's hard to get it, but yes, we can get it. I'll set it up by the time we come next. I'll set it up
White light?
with white light.
Is that what's going on with like the gas and stuff?
Exactly. That's what I'm coming to. That's what I'm coming to. All right. So, just as you have Newton's rings deliberately formed, what is happening on the road on a rainy day with the gasoline or the oil leaks? That is Newton's rings also. But because the surface is not even like this. So what exactly is happening on the road? This is the road. As soon as an oil drop falls on it, what happens to the oil drop? It spreads out. So oil spreads on the road. Now which part of the oil is going to be thickest? Where it dropped. where it dropped is going to be thickest. So what happens is the oil drop or the oil that spills on the road just spreads out like this. But this part of it is going to be the thickest. You see?
Is that like Plano convex?
It will be kind of convex, yes. Yeah, plano convex kind of thing, yes.
Plano convex.
Yeah, almost planar convex lens, that kind of effect. But then it's going to be very fine. You know, the thickness you're talking about is very, very small in nanometers. The thickness of the oil as it spreads out is very, very little. Now, what happens over here is light comes and falls here. Some part of the light bounces off from here. And some other part goes down and goes through like that. See? There creates a path difference. So this path difference is responsible for the interference that you see. You get it? So when you look at an oil patch, what light are you looking at? Sunlight. So sunlight goes and hits and then bounces to your eye. And depending upon where it's bouncing from, you see the colored patch. It's not perfect circles. It'll be kind of wavy, like it'll be like wavy because it's uneven. Now, if you drop it on a sheet of glass or something, it will be more or less uniform, right? But since the road is not uniform, it just spreads off, kind of uneven. So you will see a wavy colored patch, and that is caused by interference.
Would glass be a dense medium?
Yes. So it will be, yeah. So actually what happens over here is, even though you see oil over here and this is the road, there will be a tiny kind of a gap in between the oil and the road. So that actually kind of causes the interference to come in different styles. Yeah, but we can see that there is no dark band. It's all colored. One will be more greenish, one will be more bluish, one will be more reddish. It's kind of mixture of colors. And it looks beautiful though. And the same concept applies in soap bubbles. In a soap bubble, yeah.
Please pardon this interruption. At this time, all seniors going on the Hamlet field trip today need to report to the
Question?
All
All right. Now, on a soap bubble, okay, this is the bubble. I'm just trying to magnify the surface. So that's a soap bubble. And that's a soap solution that you see there, the thickness. It's very thin, right? It's very thin. That's a soap. That's a surface. So what happens to a light? Now that is sunlight coming and hitting here. So when it comes and hits here, the sunlight bounces off from the top and a little bit goes down and reflects from the bottom, because there are two surfaces. There is a air soap boundary and there's a soap air boundary, because inside is air. You get it? So inside is air, outside is air, and that's a soap. So you have a air soap boundary there, and then soap air boundary. So there are two boundaries very close together. So you have interference coming in. Now, if these two interfere constructively for a certain set of colors, you see that color. And at next, at some other place, you will see probably some other colors, because, out of all the spectrum, some colors are destructive and some colors are constructive. So and because it's soap solution, it kind of moves around, right? The thickness changes. Actually, the thickness changes like that because the soap is actually moving down. This part becomes thicker, and this part becomes thinner and thinner and thinner, right? And as it gets thinner and thinner, the colors change. So when you're looking at the same soap bubble, at one spot, the colors are continuously changing. Notice it? Now, what is the last color that you see before it just breaks? Just before, you can actually tell it's going to break. Huh? You can tell it's going to break by just looking at one feature. Have you seen a soap bubble? Okay, have you seen it break?
Yeah.
Have you seen any feature on the soap bubble that tells you it's going to break?
White light?
it'll be kind of blackish or grayish patch. You'll see some black patches. Not noticed?
Oh yeah, so it gets kind of like
Yeah, I mean, like you'll see some kind of a black,
opaque almost.
gray patches. Gray patches. Yeah, the best way to say is gray patches. You'll see gray patches kind of coming up. What is a gray patch? The gray patch is the thickness becomes so small, it's almost nearly zero. And when it is almost nearly zero, what happens is these two will interfere destructively, creating the black. You get it? Almost all the colors will be destructive. And so you're not seeing any colors coming from there, and so it becomes dark, that color. His jacket color. That's what it is. You'll see those patches. As soon as you see those patches, you can say, all right, it's going to pop. Yeah, if it is beautiful and colorful all over the place, it's not going to break. When it's going to break is when you see those patches coming up, then you know that the thickness over here is too thin to form any interference pattern, and so the last thing that you see is black. And why is it black? Because these are destructive. Why are they destructive and not constructive? Because this one is bouncing at a dense medium, and the other one is bouncing at a rare medium, so there's a path difference of lambda over 2.
Because it's air to soap to air.
Yeah.
Sometimes I don't know if this is like the same, if it has anything to do with it, but when you're driving in a really hot place
Okay.
or on a really hot day, and you look at the road far in front of you, and it's like
Wavy.
wavy, is that like anything to do with interference, or is that just something completely different?
Anyone to answer that question? I think we touched that point somewhere. Refraction. That is refraction. What you're seeing is the light coming through varying, density air, because it's hot down there, and it's like density is kind of gradually changing, and hot air rises also. So basically, what's happening is there is a kind of continuously changing medium there. It is not homogeneous. It's changing continuously. So the light that's coming from there is suffering refraction. It's suffering refraction. It's not a uniform kind of refraction, it's kind of wavy because the medium is changing. It's just like how, you put a coin underwater. You put a coin underwater and shake the water surface and look at the coin will be like dancing around. And that's because of uneven refraction. Yeah.
What about when you're looking at the road far away and it looks like there's water on the road?
That is called, starting with the M, mirage. Caused by TIR. What is that? Total internal reflection. Yeah. That's caused by total internal reflection. You want me to explain that?
Sure.
All right. You know what is total internal reflection, right?
Right.
When the angle becomes more than? Okay, good. So here is the road. Here's the road. And imagine there's a tree here. All right, there's a tree. And you're far away. Now, on a hot day, you have different layers of air. You have different layers of air. So those are different layers of air like that. And this normally happens on a day when it is really hot, sun is shining too much, and there's not much wind. Like it's still. Then you see this a lot, especially in the desert. You'll see this. Now what happens is like this is the tree. Now you are standing here. So how does the light come to you? How does the light from the treetop come to you? You can actually see the tree directly, like direct. Light goes straight and then comes to your eye. So there's a tree there, okay? You can see the tree. But light also goes downward. Like what happens to this light? It goes and hits here like this. Okay, tell me, which of these layers is densest?
Bottom.
Which is hottest? The bottom. Then is it the densest? That's the rarest. You get it? Because it's hot, it's expanded. And this is less hot. So this part is more dense. This is rare. So what will happen to the ray that is going from dense to rare? Which way will it bend? Away from the normal. So instead of going straight, it will bend away from the normal. You see it? What will happen to this one? Away from the normal. What will happen to this one? Away from the normal. And probably there, it hits the critical angle. Because like it's going away from the normal, but again, once it reaches the critical angle, what will happen? It won't go further inside, it will. So what will happen to this one? It bounces back up. And then it goes on, and goes on, and on, and on. And you're looking at it from here. So these rays appear to come from where? Where are they appearing to come from? They're coming from here. Look. They appear to come from here. So you'll see an upside down tree. Actually, you'll see an upside down tree.
Your mind thinks it's water. It's water.
Oh, I'll tell you about the water. You will see an upside down tree. And I'm telling you, you can see it here. I've seen it here on the roads on summer day. On a summer day, you're driving on the road and imagine there is a car far away. Just watch the car carefully. There will be an image of a car, like there will be two cars. Like that. Seriously.
Wait, does your mind imagine that, or that?
No, it is really there. Just if there's a car going far away, just look on the road just below the car and you'll see an upside down car right there.
Oh, like it looks like right behind it with water reflecting.
It'll be just like this. This is the car that you see from a distance, and you will see almost like that on the road. Yeah, you'll see the car's reflection on the road, but so it'll be an upside down thing. So this thing is going to be upside down. What if what if there is no tree? What if there is no tree? What are you going to see?
The sun.
The sky. Look. So what are you going to see is the sky. Where? On the ground. What's the color of the sky?
Blue.
Water.
And so what will you see here?
Water.
Blue color. And is the blue color still? It's not still. It's kind of wavy. Because it's not an even refraction. So therefore, you actually are seeing not water, but it's a reflection of the sky on the ground because of total internal reflection, and it is wavy, creating more water-like appearance. You get it? Yeah. That is what is known as a mirage. And this normally happens deserts a lot. When I was in Abu Dhabi, I've seen this very early, even at short distances. You don't have to look too far away because it's so hot that even like close up, I can see the watery patch. As I'm driving, I can see the water like disappearing and more water appearing. Yeah.
When I was in Dubai, I could see the water thing that you're talking about, and there I would see the reflection of like almost as if there were water, and I was seeing the car's reflection in the water. But I wouldn't just see a car's reflection without the.
No. Here also there is water.
Oh,
I mean,
okay.
the watery appearance is always there,
Okay.
and in that you'll see the you'll see that. That's mirage. All right. Now coming to another point.
Oh no, I've definitely seen that.
The next concept is called polarization. The next one is called polarization. In this, that's the last part that you're going to learn. Polarization. Or in this chapter, the last element is polarization. So what is this so-called polarization? Yes.
Sometimes they say they polarize glasses, and then then there's not a lot of sun polarized sun to house.
Okay. You'll learn more about it right now. Listen. Listen. Let me say, if I create a little gap, on the door, can you see that little gap?
Yes.
If I create a little gap on the door, and then if I pass a rope through the gap, I'm passing a rope through the gap. It's like this. So that's a door. That is a door. And there's a little gap there on the door. And I'm passing a rope through the gap. Right? Now, if I take the rope from here, hold the rope, and if I just create waves like this, transverse waves, up and down, will these rope waves pass through that slot and go on?
Yes.
As long as their amplitude
Yes.
isn't bigger than.
No, amplitude doesn't matter. You see, I'm also, which way is the transverse? Which way is, you know what is transverse waves, right? We had done this last year.
Yes.
Transverse waves and longitudinal waves like the slinky, all right?
Right.
So transverse waves. So if I'm actually going to oscillate the rope like this, will that oscillation pass through that slot?
Yes.
It will. So this one is going to pass through the slot without any problems. No problem.
Man,
It's a three-dimensional thing. Okay.
That must be done.
I still
All right, so it's a three-dimensional thing. So that's why. All right, so it goes through. Now, what will happen if I take the same rope and do it like this, horizontally, like this? Then it won't go. If I'm doing horizontally like this, nothing is going to happen
Because it's small.
because that is vertical. That allows only vertical waves to pass through, not horizontal. Do you understand? So what is that door doing to the waves? Okay, now what will happen if I take the rope in my hands and go crazy all directions?
Only the vertical ones.
Only what?
Only the.
Only the vertical will pass through. All the rest will be blocked. That's called polarization. So write down a few lines about polarization is the restriction of waves, transverse waves. Restriction of transverse waves to a single plane. That's called polarization. Polarization is a restriction of transverse waves to a single plane. Restriction of transverse waves to a single plane. That's called polarization. So, and this thing that we are having here, the slot, it's called a Polaroid or a polarizer. Polarizer. That material that actually polarizes the light, polarizes the waves, that's called a Polaroid or a polarizer. Yeah,
So, Polaroid pictures, why are they called that?
we're getting there, we're getting there. Hold on. Hold on. So now if I keep a slot like this, if I keep a slot like this and let these waves go like that, see? These are vertical waves going through. And if I keep another Polaroid here, that's horizontal. So I've got two Polaroids now, one like this and one like that. What will happen to these waves when they go through? They just get blocked. Nothing's going through. Do you see it? So vertical slot lets the vertical waves pass through. But if there's a horizontal slot, the vertical waves will be blocked. Because this one is only allowing horizontal waves to pass through, but what's coming through here is vertical, and so nothing. So what if I go crazy and just do all sorts of waves, all different angles, you know?
Won't matter, though.
pretty crazy.
What will happen here?
Only the.
Only the vertical ones will go through, and what will happen here? Blocked, completely blocked. You understand? Now,
It feels like a circle. And would they all go through?
what do you mean circle?
Well, if you had like like the door, as you said before, and you just put a big circle into the door.
just be a
You mean a circular slot?
It's just like an open
I
space.
understand, but when all the waves go through.
Polarization is going to take place. Well, listen again. I'll explain. Now, what will happen if I make this gap too big? Look. Now that's also a slot. If I take these waves and make it go like this or like this, will that be passing through?
Yes.
So therefore, definitely there is something to do with the wavelength. There's something to do with the wavelength and the gaps. The gap must be small compared to the wavelengths. Then only you can expect this polarization to happen. Now coming to light. Is light a transverse wave?
Yes.
Light is transverse. Light is transverse. Okay, when you did waves last year, you must have learned that. All electromagnetic waves are transverse. Electrical and magnetic fields are perpendicular to each other, right? You already know that. So light waves are transverse. So what if you send light through that slot? If you send light through that slot, what will happen? That slot is too big for light's wavelength. So the light will just pass through, right? Can that slot do anything to light at all?
No.
Nothing. So in order to polarize light, you need a slot that is very tiny. And if you can have a slot that's very, very tiny, just like a grating, that is called a Polaroid filter. That is a Polaroid filter. Like, can you see me through? Can you see through it? Yeah, you can see through it, but you don't know which way it is. There are lots of slots. I can't find out. I don't know which way the slots are because I can see through it. But one thing is for sure, the light that is coming through it is this. So the light that's coming from there is this. This is ordinary light in all directions. But what is coming through it is this polarized light. It's already restricted. So the stuff that's coming through it, so when I'm looking at you, ordinary light is bouncing off you, coming through it, and what is coming to my eyes is only one way polarized. Do you get it? It's one way polarized. Now if I have another one, and if I place the other one, now if I place the other one in such a way that the two of these are exactly like that. The two slots are exactly vertical, such as this. So you are able to see through it, right? What if I turn one of this through 90 degrees and make it like that? It will just stop the light completely. Look, I'm turning it through 90 degrees. And it just totally pitch black. I cannot see you through this. Although they are transparent, look. They are transparent. It's polarized, but now it sees black.
Why is it dimming when you do that?
It's gradual. Yeah, it's like, the intensity of what's going through is kind of coming down, finally it just cuts it off.
So they're not like all.
It's not sudden. Because what happens is only a component of that is passing through. A little component is passing through. And then, yeah.
So can we see that third polarized light? Once it's straight, can we see that?
You can't.
But we can see the middle one, that's one-way polarized?
Yeah, that's one-way polarized. This is polarized light.
So the glasses that are polarized have one-way polarized light?
Say that again?
Like the glasses that you buy that are polarized? This that are polarized?
I have not got there yet. Hold on. Hold on. Yeah, you can see it's completely pitch black. You can't see this. You can't see this thing. But if I rotate it like that,
You're gonna like make the same.
you can see.
Why don't they put that on that as soon as you switch it? They put that on windows.
Now this is what is used in sunglasses. Listen up. Listen. You know the day and night glasses? This is what is used in day and night glasses. There are two films, and those two films, the molecules will rotate. One rotates clockwise, the other rotates counterclockwise. So it's basically like this. You're looking through this, and when lights hit it, when light comes and hits it, it just rotates.
Are those the ones like automatically?
Automatically changes, yeah. That's called day and night glasses. So in the night, it's transparent. But when you go out in sunlight, it suddenly turns dark. Why it's turning dark is because the molecules kind of twitch and makes it that way. It's not fully like this. It's like a little bit like this. From here, it goes like that. So it becomes dark.
Are sunglasses just set for one way?
No? You mean, what do you mean
The ways
sunglasses?
are like that don't change.
Now I'll talk about what he's asking. I don't know if you have time for that. Listen. Okay. I'll explain to you. On Tuesday.